And the next presenter is Mohammad Abu Jabed, who will help us to recall chapter number 3 about time-dependent perturbation theory.
Thank you, Dimitri. So this is we covered in this part. We first derived the formula for the time-dependent functional time-dependent perturbations, and then applied the different types of perturbations, harmonic perturbations, and Fermi level. Discuss about that one, and also periodic change one. So as Levi already discussed, is almost similar, but only difference is in our case. In these cases, the perturbation is time-dependent, so we have to solve treated this one with the time dependency. So for this one, I just this is just formulation of the formula. If we consider the two-level system, I just giving an example with the two-level system. So getting the linear combination of two basis set of these two level, and then we are getting this with the time evolution part, and it is the time evolution time-dependent basis functions. And so in this case, if we want to get the further part, I just put it in the time-dependent Schrodinger equations and then solve the equations. If we solve the equation with these basis functions, finally we will get these equations in this one. And now, and after the solve with this one, we will get a time-dependent change of the coefficients CA by using this formula. And if we put the psi A on this one, and we will come up with this one, and if we put psi B, and then we will come up with CB. I mean, this is the time ddt of CB. So after the perturbation, now we are getting the change of the coefficients A and B with the time. That's our important part here. Then if we put this number, we will get a basis function on the time t with perturbations. And for the if we want to put the first order and second order, so this I am showing the first order perturbation here. If we solve the first order perturbations, you will get this this term is 0 because it's the diagonal part, and non-diagonal part is a non-zero term. So we will get simplified this two coefficient here, and if we solve the coefficient after the integration, we will get this term here. And for example, I'm just putting only one example here for sinusoidal perturbations. If we consider these perturbations, these are periodic perturbations, and we'll solve these equations, and then we will get a transition from the first part to the second part. So I'm showing this one here, sorry, first state to second state. This is the, after the solution of that one, population of the ground state and the excited state, we will get a transition probability from the ground state to the excited state. And this is the geometrical representation of the result. This is the based on the time with the populations, and this is with the periodic difference, energy difference based on this one is known as a sinc function, I guess. Yeah, this type of things. So this is the one result of the perturbation theory, and by this one, this we presented after this chapter. I presented spontaneous emissions. I solved these coefficients, Einstein coefficients, and the coefficients, and we can use these informations for emission calculations and photophysics. And thank you.
Okay, let's thank David.